Hi everyone, welcome to today's webinar. My name is Janice Su. I'm a metallurgist at Glencore Technology with the pyrometallurgy team, working on ISASMELT, ISOconvert, and other pyro technologies. Our presentation today is by Dr. Stuart Nicol. Stuart is a senior metallurgist with the Glencore Technology pyrometallurgy team, specializing in ISASMELT and related technologies. Stuart has experience in both the design and operation of metallurgical plants across multiple commodities and processes. He earned his PhD at the University of Queensland in pyroresearch, focusing his research on phase equilibria and reaction kinetics applicable to industrial operations. Stuart's current role includes the development and study of basic and detailed engineering projects, along with site construction and commissioning for the ISASMELT and other Glencore Technology-owned technologies. Thank you for joining us today, Stuart. I'll hand it over to you.
Thanks for the introduction, Janice. As she mentioned, I'm talking about process simulation and calculations, and my name is Stuart Nicol. I'm with Glencore Technology. So just first, a bit about Glencore Technology. So we're a technology solutions provider, providing technology solutions to the minerals and metals industry all over the world. So on this particular map here, you can see all the countries which have installed our technology solutions. We also work with sites and operations all over the world who haven't got our technology, particularly those within the Glencore group, but we also work with other external clients. So we're based here in Brisbane, Australia, and we've got over 100 employees and contractors, and we have been working around for a very long time here. So today we'll be focusing on the ISASMELT group of furnaces. So within this furnace group, we've got the ISASMELT furnace, ISOconvert, ISOcycle. We also have the rotary holding furnace, BBIC, VDZ, as well as some other sorts of proprietary equipment, copper elements, and things like that. So we supply this to both Glencore and companies outside of Glencore as well, and also do a lot of site support. So where have we assisted with process simulations and calculations? So on this map here, this is a map where all ISASMELT furnaces have been installed around the world. Every single one of these has been done with our process simulations and calculations. In addition to this, we've done a lot of projects and works for smelters that don't have our technology, and we do process simulations and calculations for them. And we do a lot of this, particularly within Glencore. So what exactly are these process and simulation calculations used for? So they're used at all stages of a smelter's life, all the way from when one's being built on a green field with nothing there, all the way through to that final tap when that last molten product comes out. So they can sort of be classified and look at different things. Each calculation does a different task and a different thing, and they're always customized for different purposes. So the first stage, when we design our smelter, we've got special calculations. It's about sizing your plant, sizing your equipment, looking at what you need to do what you want for the feed materials to produce the products you want. Then after that, you sort of have smelter modification. So this is where you're taking your existing asset and your existing smelting complex and adding and changing equipment with feed changes and different targets in mind for the overall smelting complex. After this, we've got our planning tools, so long, medium, and short-term planning tools. So this is about adjusting and running your plant with the equipment you have to get the highest throughput and best operation. So you've got long-term planning. This looks about the minor elements and the flows in the overall smelting complex, tuning the overall flow sheet, so adjusting one furnace to improve the other to get the overall net benefit. Then we get to short-term and medium-term planning. And this is about the individual units, or maybe one or two highly linked units. After that, we have furnace control, and this is about running our furnaces as well as possible. So I'll sort of step through these different calculations and we'll sort of describe these ones. So first of all, we'll start with the smelter design calculations. So when you look at the traditional smelting design process, you'll see a number of sorts of things coming across your desk if you engage an engineering company to do this. So first of all, you'll probably start to see a process design basis. This documents all the feed materials and all the desired outcomes from the smelting project. Then they'll develop a process design criteria. So this is built from benchmarks and surveys and discussions with equipment vendors. They build up what can possibly go on and select sorts of equipment and things that can be used and how they'll operate to build up an integrated system. From this, they take the process design basis, process design criteria, and do some basic calculations and produce block flow diagrams and process flow diagrams and stream tables as well. And so this particular approach is based on benchmarking and existing operations. The calculations are not necessarily complex, and they can be fairly simple. So instead at Glencore Technology, we do process design a slightly different way. So we've got a more complex process with more steps and more things going on. So first of all, we start with feed specifications and product specifications. So this is really important that we characterize and understand our feed and our products really well, because this has a huge impact on the energy balance and the smelter design. And a good example of this is lead and sulfur materials. So lead sulfide and lead sulfate perform very differently in a furnace. So lead sulfide requires oxygen and generates heat, whereas lead sulfate requires a reductant and consumes heat. They perform very differently. So it's really important to understand what you have in your feed to design your smelter effectively. So once we sort of figure out our feed and products and what we have going in and what we want coming out, we then just sort of build up and design our smelter. So we sort of have two key pieces of information we build our calculations on. First of all, there's plant data from both pilot or full operation. This gives us a really good understanding of the chemistry and things and the connect processes and captures a lot of the complex chemistry. We also have thermodynamic simulations. So this is used to fill the gaps, as well as early studies and early stages where we haven't yet done piloting or full-scale smelter design. From these two data sources, we obtain all the information we need and we build what we have as a flowsheet simulation. So this tells us all the materials flowing in around the smelter, all the recycle load, all the recycling loads, dusts, slags, drosses, all the things going in and around, and helps us to size our equipment, our furnaces, and everything going on. From that flowsheet simulation, we then provide our flowsheet specifications. So this is done in a number of ways: process flow diagrams, stream tables, mass and energy balance reports, duty specifications, and other sorts of documents out there, control philosophies and those bits and pieces. After this, we start to specify the equipment and provide really detailed information on the equipment you need. So this comes about in our equipment specifications. The last one as well, which we're doing in our design, is developing our plant control tools. So these tools are developed in parallel with all these calculations and design to enable the person to run the smelter as efficiently as possible. So on the bottom there, you can see that's the traditional approach, PDB to a PDC, to the PFDs and stream tables, the equipment data sheets. You can see ours with a lot more steps, and let's just get more information and design a really rigorous smelter that works. So I'll now sort of step through some of these key ones there, the feed specs, plant data, thermodynamic simulations, and flowsheet simulation to explore these ones in a little bit more detail. So that first one up is our feed and product sampling and characterization. So we collect pilot plant samples and feed samples, and we measure a range of things using design. So this is really important as the phase and the chemistry has a huge impact on that smelting design and what you need and how to run it successfully. So there's a few chemical techniques and analytical processes we do to characterize all these things. So first of all, there's bulk chemical analysis. For this, there's both XRF and ICP are both commonly used for feed characterization. There's a lot of techniques and things in there within the XRF and ICP, ICP, OES, ICP, and other sorts of things like that. You also got XRF, glass beads, press pellet. You got the EDS detectors and WEDS detectors, XRF. Phase ID, there's XRD here as well. So once we know the bulk chemical analysis, this tells us the concentration of the elements within the material. This doesn't tell us the phases they're in. And so knowing the phases is very important, particularly when we're looking at our plant samples. So to understand the phases, we do XRD. This tells us the crystalline material within the sample. So this particular technique, there's a range of ones here. Of importance is to choose the right technique, particularly when you've got pastes and sludges, as a lot of non-crystalline material here. And you have to have the right techniques to pick those up and quantify them. So this tells you the phases present and the bulk composition. Now we're doing 1 and 2, but we don't know where the minor elements sit. And so the minor elements can be different crystals and different parts of the chemistry. In your slag, is your alumina dissolved in the slag and your molten oxide solution, or is it present in spinel, or is it present in other phase altogether? So to determine where those minor elements sit, we then do element distribution and phase identification with SEM and WDS and EDS detectors. So this is very important techniques. And you also got techniques like laser blades and ICP and mass in there as well. So this sort of tells you the concentrations and where things sit. And so this is the last one there. Then lastly as well, for those sludges and amorphous materials, we don't have thermodynamic information as they're amorphous. So instead we do things like TGA and DSC, which tell us some of those energy balance informations there. So the last one, of course, is it's really important that if you get these analytical techniques done, you work closely with an expert. So here at GT, we have a number of partners who are world leaders in these techniques, and we work very closely to characterize all the materials we have to get it done really correctly. So if you choose some of these techniques, you have to do all of them, but this will give you really a good understanding of what's in your feed materials. We can then design a smelter really well. So the important one here is to get the right techniques and choose experts to do it to get the right information. Because if you build a smelter off bad data, it's far, far worse than building a smelter off no data. Things won't work, things won't function, and you'll have a lot of time and effort and money spent making it work correctly. So working with those experts is really key for this particular one. Next up is our pilot and plant data. So at this stage, we see what information we have in our library. So we've got a library from over 30 years of doing all these sorts of tests and running plants. And we try and match up some of those pilots and things we have before in our library to the new feed material. If it's very close, we can then start to design off that past test work. The important one is a lot of the full-scale plant design data. So if there's an existing operation running with the similar feed, like copper or lead, where there's a lot of ISASMELT installations, we're able to design and smelter without doing any test work. So we can use all the plant data, extrapolate it and fit it, and make it work really well. If it's a new novel feed that's a bit different, we then have to look at some of these pilot testing. So first of all, we check that library. If there's nothing in the library, we then probably have to do some test work. So there's 2 stages of test work. At the early stages of the project, we do F600 crucible testing. This gives us initial design information, particularly for the molten bath components, so the slag and the matte or the metal phase, looking at the distribution of elements in there and giving us some good understanding of that slag chemistry. After that, when we move to the next phase of the project, there's a higher level of detail required, we do F1000 pilot testing. So this is for your full-scale smelter design. It's generally higher cost and slower than the F600, but this will give you good information on, what good refractories to use, what's your off-gas system and how should you handle that there, emissions control techniques. And the other important one that we get from F1000 pilot testing is the engineers doing the design work run the F1000 pilot plant, and they understand how the process works, the chemistry, the tools, and the challenges of running it. And they take a lot of the learnings in running the equipment back to the smelter design to design a smelter that really works well. So with all these steps here, there's sometimes information missing, and we sort of have to fill that with thermodynamic information. So with this one, so thermodynamic stimulations are predictive tools. So you specify all the feed materials and some general running parameters, and it will predict what will come out of the furnace. So these thermodynamic simulations are really good before you've done those pilot tests at the very initial stages of a project. These calculations are very low cost, cheap, and fast, really easy to do. But there's lots of kinetic information which is not necessarily captured. And as well, if there's new novel feeds and low concentrations or the analytical techniques are difficult, we generally fill the gaps, those pilot and those full-scale plant, with a lot of these sorts of calculations. We also do this for a lot of detailed slag design. So a lot of the fluxing targets, slag physicochemical properties, we use these particular tools to calculate and predict. So we use both FactSage and MPE here at GT. They've got both strengths and weaknesses in different regions in their packages, so we use a blend of both to design our smelters. The important part with these packages is the thermodynamic solution models that provide the backbone for these calculation tools. And so we work quite closely with the University of Queensland here in Brisbane, as they're one of the world leaders in the phase equilibria field, which builds up these FactSage thermodynamic solution databases. And we've got a lot of custom databases which we use with them. Then lastly, once we've got all the information, so we've characterized our feed, our products, we understand the pilot, and the full-scale plant, how those run. We've got the thermodynamic information to sort of really fine-tune our designs, our models, understand our minor elements. We then build a flowsheet simulation. So flowsheet simulations are fitted parameter models. So what this means is that all the information, everything here, you have to specify. And that's why you have to go through all that effort to getting really good data information there. So these simulations provide the mass and energy balance, including the recycled streams, the tons in, tons out, the energy going in and out, and sort of tells us all the material flows within the smelter. From this, we can then sort of build up our equipment design parameters, our off-gas system requirements, waste heat boiler sizing, dust collection, things like that. Helps us to fine-tune bleed streams and things like that, so dust leaching plants. It then provides stream table information and parameters which are also used to understand the overall smelting flow sheet. So there's a number of software packages available. So both MetSim and HSC Sim are commonly used packages. The core backbone of these packages is their pure component thermodynamic information. So it's really important that you choose a package which is very accurate data and have really good reviews of the information using these packages. So MetSim is an older package. Generally, if you use this package, you'll have to fill in the data and review a lot of the thermodynamic information, as a lot of the more modern information on the solutions and the component data is not quite accurate at times. And so instead we tend to use HSC sim as this is more accurate pure component data. So the last one I'll comment here is generally these models you build up are sort of dumb models. So what this means is they don't have all the predictive capabilities, they don't extrapolate well, and they don't really help you do sensitivity analyses and understand really detailed design and optimization of the flowsheet as an integrated system. So to do this, we have to add a lot of these thermodynamic smarts to enable us to extrapolate and sort of work in between the range of conditions which those dumb models have. So how do we fit those smarts? So there's three ways which we can get smarts, which we put into our model. The first one is from our pilot plant data or our full-scale plant data, surveys and correlations. So this is basic relationships between your control variables of plant responses. So, MAC grade and, things like PSO2 and the off gas and things like that, and sort of trying to create and guess parameters that link. And you can sort of see that in the right figures there. So in the top one there, they're showing nickel partition coefficient versus iron oxide in the slag. So the challenge with these particular models and fits that we put into our simulations is they don't necessarily pick two variables that work really well together. So in that top chart, the nickel partition coefficient, this is really dependent on the furnace PO2 rather than the iron oxide in the slag. But then you have to sort of choose different parameters to get things quite nice. So there's also complexity with doing this really well. The other one approach we can take is the fundamental relationships. So this uses packages like FACSAGE and MPE that reach equilibrium, and you understand that's fundamental relationships and the fundamental links between parameters and what goes on in your furnace. So this gives you good relations, but it has got that inherent assumption that equilibrium is achieved, and also assumes that the fundamental data you use to build up these packages are correct. And there's a lot of phase equilibrium research that's still ongoing to fill in the gaps and make sure it really works. So both of these first two have some limitations. So what we do as a third one is we bring the strengths of both to provide really good relationships. So the best practice. This is where we take those plant data and fundamental relationships and try and blend the two together. So trying to fit those fundamental relationships to plant data, getting some trends and lines and sort of getting things working really well. And that's really the best way to do these ones. So this is also very useful for some of those big data or data science approaches to linking up plant data, trying to link through the subject matter expert understandings of how the smelters work. So we put a lot of these sorts of smarts into our flow sheet simulations to really understand the chemistry and really fine tune and optimize the smelter designs. So once we're doing that flow sheet simulation, we're then able to specify and design our smelter. So I've briefly run through here the steps we take to build up those simulations. And then once we've built them up, we then have all those outputs. So this is a brief rundown, and we'll sort of explore some of these other sorts of tools, particularly as plant control tools. So we just went through the first one, which was smelter design. The similar process is also used for smelter modification. So a similar sort of way of building up a model. When we're doing smelter modification, we have a lot of plant data, and we'll generally build it entirely from plant data without doing any pilot or thermodynamic simulations. We can all build it up off that plant data itself. The next one's planning tools, long-term, medium-term, and short-term. So these are generally somewhat similar, different sorts of calculations. The important difference between the timeframes is the complexity and how integrated the calculations are. So for longer term, we look at this entire smelter. For the short term, we'll look at the smaller systems. And last, we've got those plant control tools, the furnace control tools. So these are used to really run the smelter well. So I'll step through those planning tools, and we won't sort of cover in much detail those furnace control tools, just because these are very customized, very tuned for each operation, each furnace, each condition. They're generally integrated within the DCS or have tools linked to the DCS and the database systems within the plant, and they're very proprietary tools. So we won't cover those as a result. So first up, we have our long-term and medium-term planning. So a lot of these sorts of calculations and simulations are done to understand how the recirculating loads and the overall smelter will perform in coming months when we've got a large supply of material. So it's very important here to understand the recirculating loads and how to optimize the overall flow sheet. So do you change your MAC grade target in your ISASMELT furnace to optimize your ISOconvert? Do you bleed a bit more minor elements? How do you split and manage your overall smelter for the new feed mix? So it's very important to look at your integrated system. In particular, calculations here are generally those fitted parameters we touched on before, things like the HSC sim models. And they sort of look at the integrated system and you build them up in a very similar way. And we generally develop these in parallel with those initial flow sheet simulations. We can hand those models over after the initial plant design. Then when we look at the short term, this is about how a single furnace works as a single piece of equipment. So this doesn't look at the integrated system. Instead, this is looking at, on the short term, running that one unit as efficiently as possible. So we only look at a single furnace on the short term because the amount of recycle streams it generates, dusts, drosses, and intermediates on the hour to hour doesn't have a huge impact on the overall smelter. But when we look at the longer term, it will. So when we get down to those day to day or maybe even week to week, we're just looking at that single furnace doing the single thing and running it really well. So the things we sort of tune is our KPIs and our targets within our furnace. So things like our fluxing targets, our temperature targets, fuel and coolant requirements, and our minor element controllers that have hit the required specs for our products. So you can see there we have our MPE tool here. This is one tool that we use quite commonly and is very successfully used in a range of operations. Generally, Excel-based tools are quite good here, and they're very customized for the particular furnace that's being used. Each furnace behaves very differently. So we can see here, this is the general flow sheet. So the MPE feed blending approach, changing our KPIs of our furnace, enables us to accept a much wider range of feed compositions. So we're no longer constrained to a really tight, narrow range of feed blend requirements. So the alumina requirement's gone, the lead requirement's gone, other sorts of things like that, completely thrown out the window because we ran our furnace very differently. So that MPE tool enables us to reselect and redesign our slag chemistry and reselect and redesign our minor elements and how they perform. So we run our MPE tool to these alternate targets, so slag physicochemical properties and other sorts of conditions there, and we then redetermine our new KPIs. We then provide those new KPIs to our operators to then run the new feed blend or feed mix and optimize that furnace well. They then run that new material, they fine-tune it during the operation, and then we rerun our MPE simulations to further optimize that recipe, which we give them for a new feed blend. So this enables a smelter to run for different constraints as the market conditions require. So for example, you can take more parcels of a different sort of a high cobalt or different things in this month, and as the market conditions change, you can take more of other things. So it enables you to sort of swing around what feed materials you take to really maximize performance in your overall smelter. So sort of just briefly gone through those planning tools, and we'll now sort of explore some case studies to look at a little bit more detail of some good practices through these ones. So first of all, we'll look at those overall flow sheet simulations. So I sort of briefly touched on those software packages, MPE, HSC Sim, FactSage, as well as MetSim. So the problem here is we're looking at that whole smelter, integrating, making it work all together as a system, it's a cohesive system doing a mass energy balance. So you can see in that picture there, that's all the lights of Mount Isa mines. And you can see there's a large number of equipment, plant, buildings, and things going on. And we want it to all work together. So what we do is we build up a flow sheet simulation. So it requires all our pure component data and a lot of relationships between material flows in and out, accumulation equals input minus output. And so we do all these sorts of bits and pieces, and we build up all these formulae. So lots of streams, lots of formulae. We build up in Excel every single little cell. We got a formula there. We also have to input all the thermodynamic information for our pure components, heats of formation, heats of mixing, enthalpy, and functions like that. We have to build it all up, do all our literature reviews, and put all the parameters into our model. So this is very time-consuming and laborious to do. Every single cell needs to be put in, and formulas need to be input for every single cell. Because there's lots and lots of cells, because a smelter has lots and lots of streams and lots of things going on, it's going to be extremely difficult to error check because of the sheer complexity of the calculations. And because of the sheer complexity with the number of cells, number of formulae, number of things going on, it's very difficult to hand over to another engineer to use. So the consequence of this is that simulations generally filled with errors. There's lots of little mistakes, unintentional of course, but because of the sheer number of formulae, there's going to be a higher likelihood of there being a mistake just because of the number that's in there by nature. The other one is going to be very, very hard to hand over to others because of this sheer complexity. It's very challenging to hand over to others. It's very difficult to do. So I've seen these sorts of Excel spreadsheets for a complete smelter done, but they're generally very difficult. I probably wouldn't recommend it during these underlying issues present. Instead, what we have is these automated packages. So things like HSC Chemistry, HSC Sim, MetSim, SysCAD, Ideas, LIM. There's dozens of programs out there. So these take a while to learn how the packages work, but they're really good because they provide a graphic user interface and a lot of the background information, background calculations, all the material flows in and out, all those sorts of formulae are already pre-programmed into these packages. And you just need to put in the core information required to get your simulation going, all the sort of basic control loops and things there. All the thermodynamic information has already been checked and input into their databases. But as I mentioned, just make sure that that database is accurate and modern and up to date. So this means that you can build a model fairly quickly, very quickly when you're really well trained. You can build it accurately, you can document it well. It's easy to check and transfer to other engineers and produce other engineering deliverables from these calculations and simulations. And as well, by putting on those smarts, which we talked about before, which is very easy in these packages, we can start a lot of the sensitivity analysis and a lot of the feed other sorts of studies and things like that. So these packages really automate and improve your calculations, much more so than those basic Excel ones. So the next one we'll talk about is a batch simulation of a copper converter. So batch simulations are a unique sort of pyrometallurgical calculation. So with batch furnaces, we charge materials and do some things, and the composition within the furnace, temperatures within the furnace change over time. And like most furnaces, we want to control our temperature well and control the chemistry really well. But because of the transient nature, things change on a minute-to-minute basis. This makes it very difficult to calculate these really well. And there's very unique calculation solutions here. So what we use typically for these batch calculations is proprietary in-house models. So on the right there, you can see some charts from a batch simulation we did for a client. This was a Peer-Smith converter. Now particularly interested in the zinc performance for the flowsheet and optimize the removal and rejection of their dust. So with this particular batch proprietary tool, we look at the temperature at all times within the furnace. We can find temperature peaks, and we can then add coolant and guide operations on how to run their furnace well for these conditions. You know, adding reverts or adding fuel to maintain the temperature well. We can identify temperature spikes before they're going to happen, and we can tune the chemistry to really get the performance of those variable and changing concentrations within the phases. So what these calculations enable us to do, we can then design the batch for specific chemistry targets. We can design it for transient temperatures, fix those temperature spikes, and when things drop out and things like to freeze, we can add fuel when we need it to, or know it before when we need to do it. We can do a lot of these sensitivity analyses and redesign and re-optimize our furnaces, things like blowing rates and bits and pieces like that one there. And the last one as well is we can develop these tools for production purposes as well. So new charges, new feed, you can then re-understand and re-optimize your charges if you're changing mat grade or other things around your smelter. So this is quite useful tools, but they're very proprietary, very in-house. We have developed these quite well for a number of people. So the last thing I'll touch on is what we call the success zone at Glencore Technology. So for our process calculations, you sort of have to take three things into account to get a really good calculation. So first of all, they must be fundamentally backed. So that means the chemistry must work, the thermodynamics must be there, the chemical reactions must be there, the chemistry must be really well known and fundamentally correct. From that, we also need the process and the furnaces to be operationally practical. So what that means is someone must be able to run it. So, you know, you're charging it in batches which are reasonable, you're tapping reasonably things, and things are just really able to work, able to function. People can do stuff. Then lastly, it must be a robust design. So what this means is it must be robust, reliable. You know, it can take highly variable conditions. It's easy to run and, you know, works well. So whenever we do this calculation to design, we work as an integrated team to make sure we hit this success zone. So we work with a range of experts in our team to sort of make sure we hit that every time. So the last thing I'll mention as well is we do offer training and packages in these sorts of programs. So we can do HSC Sim, FACT8 MPN, training and calculations and tools. We can develop tools with sites, and we do this quite often. And so please reach out if you'd like to talk to us about what we can do here for you. So lastly, thanks for listening into this webinar. I hope you learned some new things. So I'm Stuart Nicol, that's my email there, and that's the ISASMELT team, and we'll all like to thank you for listening in today.